This part of the story is about the magnetic force on a current carrying conductor. So the setup is as follows. Think of a piece of conducting material like a wire or a cable, something like that, and then there is an electric current that is flowing through it. Now suppose that enters a region where there is a local magnetic field. Now we know that every flowing charge inside of that conductor is going to experience a magnetic force that is proportional to the charge and to V cross B, where V is the velocity and B is the magnetic field. So since each charge inside the wire is going to experience that force, that means overall the whole conductor is going to experience that magnetic force. And what we want to derive now is an expression that doesn't depend on the amount of charge, but rather depends on the amount of flow, which is the electric current. So we think about this QV part and we say there is some amount of charge that is moving from this side to this side through this DL, which is an element of length along the direction of the flow of the current. And I say there's overall some amount of charge moving from this side to this side. And that amount of charge is traveling with some velocity that I can think of as the distance that it travels divided by the time on average. So I can write the V part as dl over dt. But if you recall, the definition of the electric current is the amount of charge that flows through a cross section per unit of time. So this Q over T part, that's the electric current. So the contribution to the magnetic force for this little bit of element along the length of the wire is given by IdL cross B. And if I want to find the force over the full conductor, then I would have to integrate over the forces that are applying to every little dl along that segment. This expression simplifies greatly when the line segment is a straight segment and the magnetic field is uniform, because this cross product then would have a simple expression to it. And the integral just becomes an integral of dl, which is L. So overall, if I have a straight segment carrying a current I in a magnetic field that is uniform, then I get that the magnetic force is proportional to the current, the amount of flow. And remember that conventional current, we're thinking about positive charges flowing. So here we're thinking about the conventional current. How much is the amount of current that is flowing through a cross section of that segment of wire? L is the length of the segment that is within the magnetic field. So only the pieces within the magnetic field where the charges are moving, experiencing magnetic field, then will experience a force. And then B, of course, represents the magnetic field strength or the magnetic flux density. And theta here is the angle between the direction of the flow and the direction of the magnetic field. Just like for individual charges, theta was the angle between the V and the B, or the velocity and the magnetic field. In this case, the theta is the angle between the direction of the flow, which is the current, and the magnetic field. This will give you the magnitude of that magnetic force. How big is that force? To find out the direction, you can use the right-hand rule. Of course, you can always do the cross product to start with. But if you just want to find magnitude and direction separately, you can find the magnitude using ILB sine theta. And the direction you find with the right-hand rule, the force right-hand rule. So remember that the thumb points along the direction of the flow of the charges, the direction of the movement of the charge. So here it points along the direction of the conventional current, and the conventional current is the direction of flow of quote unquote positive charges. The magnetic field, of course, always points, in this case, is pointing downwards because it's pointing always from the north to the south poles outside of the magnet. So if I put my right hand thumb along the direction of the flow of the current, I put the rest of the digits along the direction of the magnetic field, then out of the palm of my hand would be the magnetic force on that current segment. So this part of the wire here, if I connect it to a battery, so the current will flow from the high potential to the low potential. And when it's sitting in a magnetic field, the current is flowing this way, the magnetic field is going downwards, so the force would make the wire swing in this direction.